In this class, we will give an introduction to Laplace transform. A transform in general is a change in a mathematical description of a physical variable in order to facilitate computation. So what we do here is we transform from one form to the other. So if it is the representation of the function in time domain, which is in terms of f of t, we try to represent this in terms of the frequency domain. So in the case of the Laplace transform, if the time domain representation is, say, f of t, in the frequency domain it will be f of s. So what we have done is we have changed the description of this physical variable from one form to the other. Okay, so let us define the Laplace transform. Mathematically, the Laplace transform of a function f of t is given as L f of t to be equal to f of s, which is equal to 0 to infinity f of t e power minus st dt. So in this case, this s is basically a complex frequency which is equal to sigma plus j omega. In this equation 1, this parameter, that is exponential term e, is dimensionless, but s, that is the complex frequency, is having dimensions of frequency, and the unit is second inverse. So in the Laplace transform of the function, what we have done here is we have transformed from time domain to the frequency domain, and in the frequency domain we represent this as f of s. Now if you look at the limit of the integration in equation 1, the lower limit is 0 and the upper limit is infinity. The lower limit can also be minus infinity. So if the lower limit is minus infinity and the upper limit is infinity, we call such type of transform to be the bilateral Laplace transform. But the equation that you see here is having a lower limit of 0 and an upper limit of infinity, and these kind of transforms will be called as the unilateral Laplace transform, and we are going to mainly study the unilateral Laplace transform, where the limit of integration will be from 0 to infinity, and these are very much useful, especially in the circuit applications when we do the analysis. So moving on, we will look into the singularity functions. Singularity functions basically are the discontinuous functions which are discontinuous at singular points. So there are three types of singularity functions, that is the unit step function represented as u of t, delta function represented as delta of t, and the third one is the ramp function represented as r of t. So let us look into each of these individually. The first one is the unit step function represented as u of t. Mathematically, this unit step function can be written as u of t to be equal to 0 for t less than 0 and 1 for t greater than 0. If I have to represent this in the form of the waveform, the unit step function can be represented as u of t along the y-axis, t along the x-axis, and you have u of t to be equal to 1 for t greater than 0 and 0 at this particular point. So if you have to clearly look at this, you will observe that this basically corresponds to t equal to 0 plus, and this corresponds to t equal to 0 minus. So at t is equal to 0 plus, that is greater than t is equal to 0, you will observe that the value is equal to 1, and at t is equal to 0 minus, the value is equal to 0. So in short, what I want to basically tell here is the unit step function u of t is not at t is equal to 0. Okay, so if I have to write in terms of negative and positive values of t, I can write this as u of t is equal to 0 for negative values of t and u of t is equal to 1 for positive values of t. So you can represent this in this way: u of t to be equal to 0 for t less than or equal to 0 plus and 1 for t greater than or equal to 0 minus. Now sometimes while representing the unit step function, there can occur some sort of discontinuity, okay, other than t is equal to 0, because here you can see we have represented the waveform corresponding to the time interval t equal to 0, right? So there can be discontinuity in terms of the occurrence of the signal. Then we can say that the signal u of t occurs at t is equal to a. Then we can express this as u of t minus a. Let us try to represent this signal. So I can represent this as u of t minus a, and the signal occurs at the interval a. So if you observe, this would be the waveform having an amplitude of 1, and mathematically this signal u of t minus a can be written as 0 for the time t minus a less than 0, or I can write this as t less than a, and this will be equal to 1 for t minus a greater than 0 or t greater than a. So basically, if you have represented a signal u of t minus a, you can see this signal u of t is delayed by the time a. Okay, it has been delayed by the time a. Similarly, we can consider the discontinuity if you have a signal u of t plus a. So in this case, the waveform or the signal can be represented as u of t plus a will be equal to having an amplitude 1 and this interval is 0. So basically this signal u of t plus a can be mathematically written as equal to 0 for t plus a less than 0, or I can say t less than minus a, and equal to 1 if t plus a is greater than 0 or t is greater than minus a. So this signal is advanced by an interval of a, whereas this signal is delayed by an interval of a. Now this unit step function can sometimes also be called as the step function. We can use this step function to represent the abrupt change in voltage or current, and mainly these kind of abrupt changes that you observe, they tend to occur in the control engineering systems and the digital systems. So it will be very useful for us to represent the change in voltage or current in terms of the unit step function. For example, let me write this as a signal v of t equal to 0 when t is less than a and equal to k when t is greater than a. And this particular signal can be expressed in terms of a unit step function as v of t to be equal to k into u of t minus a. Here k corresponds to the value of the signal, and this is some positive value or a negative value. Okay, so the interval that you observe here is corresponding to a, so that is why we have represented u of t minus a in this case. So if you observe, this very much matches with the waveform corresponding to the one which we have seen here, that is u of t minus a, but the only difference is that we have an amplitude in this case to be equal to 1, whereas here we have the amplitude to be equal to k. So this is one example which shows you how we can represent the change in voltage in terms of the step functions. We call this as unit step function, that is because it's having a value of 1. In this case we have considered the value to be equal to k, so I have considered only the representation of the step function. Now the next type of singularity function that we have is the delta function, which is delta of t, and this can be also called as the Dirac delta function or the unit impulse function. Mathematically, this delta function is given by delta of t to be equal to the derivative of the unit step function. So from the derivative of unit step function we obtain the delta function, and we can express this as equal to 0 for t less than 0, undefined if t is equal to 0, and equal to 0 for t greater than 0. So basically this is a very short duration pulse of unit area. I can represent this particular signal as equal to delta of t, and let me point out the arrow mark in order to show the amplitude equal to 1. Integration 0 minus to 0 plus delta of t dt is equal to 1. So as shown, mathematically we obtain a short duration pulse of unit area wherein t equal to 0 minus denotes the time just before t is equal to 0, and t is equal to 0 plus corresponds to the time just after t is equal to 0. The area under the pulse that you can see is equal to 1, so you have to ensure that whenever you draw the signal, you specify the magnitude 1 beside the arrow, so that it's very clear that you have marked the delta function. Okay. Moreover, this signal, this magnitude value equal to 1 basically indicates the strength or the weight of the pulse. Okay. So sometimes in the signal they can specify that signal strength or the weight to be more than 1. So accordingly you need to draw the waveform. Okay. So let me just give you an example of how that happens, and we will have a better understanding. So let me consider the example where they have specified the impulse functions 2 delta of t plus 2, phi delta of t, and minus 2 delta of t minus 3. So if I have to draw this entire signal, I can see here, let me consider this to be the origin. Whenever you have the signal as t plus, it is advanced in time. Whenever it is t minus, it is delayed in time. We have seen that from the unit step function. So the same concept is applicable here as well. Plus, t plus corresponds to advance, t minus corresponds to delay in time. If you look at this particular signal phi delta of t, it is neither delayed nor advanced in time, so that means it is on the point of origin. So I can write this or draw this as the signal delta of t. Since it is having a weight equal to 5, I need to mark that, and this will be equal to phi delta of t. Always remember, as I specified earlier, we need to specify the arrow, beside that specify the weight for the delta function. Now the second one that you have is 2 delta of t plus 2, and this is advanced in time, so it will come in the negative side of the x-axis. So this is minus 2, and I can write this signal as 2 delta of t plus 2. Then this is having a magnitude to be, or this is having the weight to be minus 2, so that is why it will come on the other side of the y-axis. Okay, and this is t minus 3 corresponding to the delayed in time, so it will be plus 3 here, and this signal is having a weight minus 2, and then you have delta of t minus 3. So as it is observed, the impulse signal in this case has a weight of 2, in this case has a weight of 5, and here it has a weight of minus 2. Moving on to the next important property, that is the sifting property. This is one of the properties of the unit impulse function. Okay, and this can be represented as integration t1 to t2 f of t delta of t minus t naught dt is equal to f of t naught for t naught between t1 and t2, and it is equal to 0 otherwise. So this property is very much applicable for the finite t naught and any signal f of t that is continuous at t is equal to t naught. So we will be utilizing this shifting property when we solve the numericals. Okay, so any signal that is being multiplied with a direct delta function which is delayed in time or advanced in time depending on the value of t naught, we have to consider the function to be f of t naught. Now, integrating the unit step function will result in the ramp function, that is r of t. So I can represent the signal r of t to be equal to minus infinity to t u of tau d tau to be equal to t into u of t. Or in general, I can represent the ramp signal r of t to be equal to 0 for t less than or equal to 0 and equal to t for t greater than or equal to 0. So if I have to represent the ramp function, I can represent this as for t less than 0 it is 0, and for t greater than 0 it is equal to t. So you will have a slope which is equal to 1. So what you observe is that the ramp basically is a function that changes at a constant rate. So I can consider this ramp function also to be delayed or advanced in time. So if I have to represent r of t minus t naught, I can represent this as 0 for t less than or equal to t naught and equal to t minus t naught for t greater than or equal to t naught. So if I need to represent the graph or the waveform, this will be equal to the signal which is being delayed in with the slope equal to 1, and this duration is t naught. In a similar manner, if I have to represent the signal r of t plus t naught, that is a signal which is advanced in time, then I can represent this as equal to 0 for t less than or equal to minus t naught and to be equal to t plus t naught with t greater than or equal to minus t naught. And graphically I can represent this as, this is 0, this is minus t naught with the slope equal to 1. So this is advanced by t naught and this is delayed by. So I can write this as r of t plus t naught, and this is r of t to be equal to r of t minus t naught. Okay, because the original signal r of t was what? It was at the origin, that from this point you had a slope equal to t, whereas in this case it is delayed by t naught and in this case it is advanced by t naught. Now next, let us look into the relationship between the singularity functions. We have seen 3 singularity functions: the unit step function, the delta function and the ramp function. And to write the relationship between all of them, we have the delta function, delta of t to be equal to obtained by taking the derivative of the unit step function. So the next one that we saw was the ramp function, which we said is obtained by integrating the unit step function. So I can also write this as, in terms of the derivative, as u of t to be equal to derivative of the ramp function. Or I can represent it in terms of integration as you can see the relationship u of t to be equal to integration minus infinity to t delta of tau d tau, that is this one, r of t to be equal to integration minus infinity to t u of tau d tau. So these are the various relationships between the three singularity functions. Next we'll move on to the functional transforms. Functional transforms basically is simple Laplace transform which is of a specified function. So here what we do is we generally assume f of t to be equal to 0 for t less than 0. So this is the general assumption that f of t is equal to 0 for everything along the negative side of the axis, that is for t less than 0. So we look into the first one, that is decaying exponential function. The decaying exponential function is given as f of t to be equal to e power minus at into u of t, where a greater than 0 and u of t is the unit step function. So you have Laplace transform of e power minus at u of t to be equal to f of s, and this is computed as 0 to infinity. That is because we are considering the unilateral Laplace transformation, that is why the limit is 0 to infinity f of t e power minus st dt. So let me do the computation. Let me substitute for f of t 0 to infinity e power minus at into e power minus st dt. This can be written as integration 0 to infinity e power minus s plus a t into dt. If you remember, integration of e power ax dx is equal to e power ax divided by a. So same thing we will apply here. We can write this as f of s to be equal to e power e power minus sa minus s plus a into t divided by this entire term, that is s plus a. So there is a negative sign here. Let me bring the negative sign outside, and this will be s plus a. Let me substitute the limits. T is equal to 0 to infinity. So if you can again recall, we have e power infinity to be equal to infinite, e power minus infinity is equal to 0, and e power 0 to be equal to 1. So on substituting, we get e power minus infinity, so this entire term goes off. So I can write this as f of s to be equal to minus 1 by s plus a into e power minus infinity minus of e power 0. So this entire term goes off because as you can see e power minus infinity is 0 and you have a negative minus 1. So finally I get the expression as f of s to be equal to 1 divided by s plus a. So in the similar manner, we will be computing the Laplace transform of other functional transforms. The second one that we have is the unit step function. So we have f of t to be equal to u of t. Laplace transform of u of t will be equal to f of s, that is equal to integration 0 to infinity f of t e power minus st into dt. So here it is integration of 0 to infinity u of t e power minus st dt. If you remember, when we started off with functional transforms, we said that we are considering f of t to be equal to 0 for t less than 0. And we have seen previously when we looked into the singularity functions that the unit step function is having a value of 1 corresponding to t 0 minus 0 plus this point and this point. So we are considering for t greater than 0, right? So if t is greater than 0, the value of this particular signal is 1. Hence I can write this as equal to 1, and it will only be 0 to infinity e power minus st into dt. Previously we have seen what is integration of e power ax, that is equal to e power ax divided by a. Using the same thing here, this will be e power minus st divided by minus s, substituting the values 0 to infinity. E to the power infinity is equal to infinity, e power minus infinity is equal to 0, and e power 0 is equal to 1. In this case it is e power minus infinity, so it will be the first term completely equal to 0. Let me bring this minus 1 by s outside. So this is 0 minus e power 0 is 1 minus of minus. So you get finally the expression f of s to be equal to 1 by s. Moving on to the third type of functional transform, that is the impulse function. The impulse function is represented as f of t to be equal to delta of t, and taking the Laplace transform of delta function, we have this as f of s to be equal to integration 0 to infinity delta of t e power minus st dt. Now in the case of the delta function, we are considering the value at t is equal to 0, and this is having a weight equal to 1. So directly substituting 0 to infinity, it is 1 into e power minus st dt, right? So since the value exists only at 0, now I can change the limits of this particular integration only to t is equal to 0. It is not ranging from 0 to infinity, it is only the function at t is equal to 0. So I can write this as e power minus st, only the duration is t is equal to 0. So the concept of applying integration does not come into picture in this case, because we have the term only at t is equal to 0. So on substituting this, I get this as e power 0 to be equal to, next is the sinusoidal function. The sinusoidal function can be represented in two ways, either in terms of sine or in terms of the cosine. Let us do the substitution for the sine, then similarly we can obtain for the cosine. So we have f of t to be equal to sine omega t for t greater than or equal to 0. Taking the Laplace transform of this would be difficult directly. So what we will do is we will try to represent this sine omega t in terms of the Euler's equation. So we have the Euler's equation as sine x to be equal to e power jx minus e power minus jx divided by 2j. So I can write this equal to 1 by 2j into, in this case x is equal to omega t. So I can write this as e power j omega t minus e power minus j omega t. To simplify this still more further, if you remember, just now we have computed the Laplace transform of e power minus s plus a t, right? So what we obtained was 1 by s plus a. So in similar steps, if we are to compute the Laplace transform of e power minus at, okay, Laplace transform of e power minus at, we get this as 1 divided by s plus a. So here a is nothing but corresponding to j omega. Okay, so I can write this as Laplace transform of sine omega t to be equal to f of s, which is equal to 1 by 2j, I can bring it out, integration 0 to infinity e power j omega t minus e power minus j omega t e power minus st dt. So we have seen what is the Laplace transform of e power minus at. So in similar steps, if I have to compute the Laplace transform of e power j omega t, this will be equal to 1 divided by s plus s minus j omega. Why minus? Because it is positive here, so this will be s minus j omega, or let me do it in terms of steps. This is basically what this will be: integration 0 to infinity e power j omega t e power minus st dt. So I can write this as integration of 0 to infinity e power, let me bring this common outside, s minus omega j omega into t dt. So this is e power minus s minus j omega t divided by minus of s minus j omega 0 to infinity. So when you do that, Laplace transform of e power j omega t will be equal to, when you put e to the power infinity, that is minus infinity in this case, it will be equal to 0 minus of e power 0, that is 1. So you have a negative sign here, then you are considering the second part of the expression. So this will be equal to 1 divided by s minus j omega, right? If I am considering e power minus j omega t, the final expression will be 1 divided by s plus j omega. So considering that, since Laplace transform of e power j omega t is equal to 1 divided by s minus j omega, and Laplace transform of e power minus j omega t to be equal to 1 divided by s plus j omega. Therefore, you can write this as Laplace transform of sine omega t to be equal to 1 by 2j into 1 by s minus j omega minus of 1 by s plus j omega. Now, using the square formula, you have a minus b into a plus b to be equal to a square minus b square. So use this and substitute this further. So I can write this as Laplace transform of sine omega t to be equal to f of s, which is equal to 1 by 2j into, let me cross multiply this will be s plus j omega minus s plus j omega divided by s plus j omega into s minus j omega. So as we have seen previously, a minus b into a plus b is a square minus b square. So this will be 1 by 2j into 2j omega, because this s and minus s gets cancelled. This will be s square minus j square omega square. So you have the term 2j getting cancelled with 2j, and what you are left with is omega divided by s square. You know j square is equal to minus 1. So minus 1 into minus 1 is plus s square plus omega square. So in similar terms, we can find out the Laplace transform of a signal cos omega t. So in this case, you have to remember the Euler's equation for cos omega t is cos x is equal to e power jx plus e power minus jx divided by 2. So here, as per the equation that we write, x is equal to omega t, and I can represent this as equal to 1 by 2 e power j omega t plus e power minus j omega t. And if you use the similar steps like the one which we have computed, you have the equation to be equal to f of s is equal to 1 by 2 integration 0 to infinity e power j omega t plus e power minus j omega t into e power minus st into dt. So you will write this as 1 by 2. This is 1 divided by s minus j omega plus 1 divided by s plus j omega. So on cross multiplying and substitution, you will get this as 1 by 2. This will be s plus j omega plus s minus j omega divided by s square plus omega square. You can clearly see j omega getting cancelled with j omega. You have 2 here, s here, and there is a 2 here, so you can see that 2 and 2 gets cancelled, and finally you get the expression to be equal to f of s is equal to s divided by s square plus omega square. So this is the way we compute the Laplace transform of various equations, and mainly we have looked into some of the useful functional transforms which will be helpful for us to solve the numericals. I will not be doing for all of them. So we have already seen 5 different functional transforms. So let us tabulate some of the commonly used functional transforms that we have. So you have the function f of t. As I told, functional transforms we will be considering for t greater than or equal to 0, and we are going to compute its Laplace transform. So some of the pairs that we have seen, we'll just jot it down. We looked into delta of t, that is corresponding to 1 in Laplace domain. Then we looked into u of t, which we computed as 1 by s. T will be equal to 1 by s square. E power minus at will be equal to 1 divided by s plus a. Sin omega t is equal to omega by s square plus omega square. Cos omega t is equal to s divided by s square plus omega square. T to the power n will be equal to n factorial divided by s to the power n plus 1. T e power minus at will be equal to 1 divided by s plus a the whole square. E power minus at into sin omega t will be omega divided by s plus a the whole square plus omega square. E power minus at cos omega t is equal to s plus a divided by s plus a the whole square plus omega square. So you may try some of the functions which we have not done and see that what you get on the right hand side in the Laplace domain. So remember these important transform pairs which will be very useful for us when we are going to solve the numericals.